All right, welcome back. We're going to jump back for a minute and go back to section 2.8 that we hadn't covered before, because the second part of it, function composition, we will need very shortly in the future. But first, let's talk about what they call algebra functions, or what I might call arithmetic of functions. This is just doing your basic arithmetic operations of addition, subtraction, multiplication, and division, but now to functions instead of numbers. So given two functions, f and g, we can define some new functions as follows. F plus g is a function which takes for each x and evaluates f of x and g of x, and then adds those two numbers together. So f plus g of x is f of x plus g of x. Similarly, f minus g of x is the function that takes x and evaluates f and g and then subtracts the two values. So we get f minus g of x is f of x minus g of x. Okay, this is the same kind of pattern over again. F times g of x is a function that takes for each x and gives you the number f of x times g of x. And last but not least, f divided by g of x is the function that takes x and gives you f of x divided by g of x. And note that this last one might have some domain issues. It can't be the case that g of x equals to 0, because then we would divide by 0, right? So provided that g of x doesn't equal 0, this function is well-defined. OK, so let's do a couple of examples. So if f of x is 4x minus 3 and g of x is 7x plus 14, let's find f plus g of x. Well, we just take the expression for f of x and add it to the expression for g of x, and then we can combine like terms. So we get 11 whole x's and then 11 constants as well. So we get 11x plus 11. OK, f minus g of x, this one we got to be a little bit more careful about. When we do our subtraction, we have to subtract the entire expression for g of x. So we'll have 4x minus 3 minus the quantity 7x plus 14. So let's see, we'll get 4x minus 7x gives us minus 3x. And then minus 3 minus 14 gives us minus 17. All right. And then f times g of x. This one we get by multiplying the two expressions. OK, well, now we'll do the FOIL method here, right? And so 4x minus 3 times 7x plus 14 gives us 28x squared from the first terms. And then plus 56x from the outer terms. And then minus 21x from the inner terms, and then minus 42 from the last terms. And so we can combine these two together in the middle here, and we simplify the expression to 28x squared plus 35x minus 42. OK. F divided by g of x just looks like 4x minus 3 divided by 7x plus 14. And one issue we have to take into account here is that 7x plus 14 is not allowed to be 0. So there's one x value that we have to exclude here. 7x can't equal minus 14, which means that x cannot equal minus 2. OK. In the next example, they'll ask us to do the same thing, but they'll ask us, instead of saying just for general x, they'll give us a specific x and ask us to find some new function evaluated at some particular x value. So they have here s of x is x plus 3, and t of x is x squared minus 4. They ask us to find s minus t of negative 5. So I evaluated s at negative 5, and I got negative 5 plus 3, which is negative 2. And then I evaluated t at negative 5, and I got negative 5 all squared minus 4, which gave me 21. And now to find s minus t evaluated at negative 5, I simply have to subtract 21 from minus 2, which gives me minus 23. OK. The next piece, they ask us to find s divided by t of 2. So we'll evaluate s of 2 to be 2 plus 3, which is 5. And t of 2 is 2 squared minus 4, which is 0. So then s divided by t of 2 is 5 divided by 0. But 5 divided by 0 is undefined. So, so this number here is nonsense, okay? In other words, we might say that 2 is not in the domain of s divided by t. So speaking of domains, what's going on with this? If ever we combine two functions like this, to f plus g, f minus g, f times g, or f over g, we have to make sure that we respect both of the domains of those functions. So what we mean here is that the domain for each of f plus g, f minus g, and f times g is going to be the intersection of the two domains. So in order for an x value to be in the domain of one of these first three ones, it has to be in both of the domains of both f and g. Okay? The same rule applies for f over g, but then there's an extra stipulation on top of that we have to exclude the x values that make the bottom g of x equal to 0. So let's watch it go here. In this example, they give us f of x is the square root of x minus 3. And g of x is 1 divided by x minus 5. And they want us to find the domain of f plus g. Well, we'd like to find the intersection of the domains of each of these functions. So for f of x, remember, in this class, we're going to ignore complex numbers and imaginary numbers for the rest of the term. So anytime we take a square root, we need it to be of a non-negative number, because square roots of negative numbers give us this imaginary nonsense. So we would, in particular, need that this expression x minus 3 that lives underneath the square root sign needs to be bigger than or equal to 0. And thus, we can solve this inequality to say then that x needs to be greater than or equal to 3. OK, so already we know then that the domain of f plus g is going to be, at most, the set of x that are bigger than or equal to 3. OK. How about the domain of g, though? It looks like there's maybe one x value that's no good for g of x. We cannot have the bottom equal to 0, so we cannot have x equal to 5. OK, so this is one other x value that we need to exclude from the domain of f plus g. So we need to have all the x that are greater than or equal to 3 except for x equals to 5, because that one is no good for g of x. So in summary, then, I guess that gives us two intervals. The interval from 3 to 5 that includes 3 but doesn't include 5. And then union with the interval from 5 to infinity, and of course, not including 5. So that's how this domain works for f plus g, f minus g, f times g. And in the case of f over g, you also have to exclude any values that make g of x equal to 0. So come back next time, and we will discuss composition of functions, the second part of this talk. And we'll be using composition of functions more often than not, I think, when we proceed into chapter 4. So it's a good one. We'll see you then.